I've stopped it. Okay. All right. So let's see how we calculate the accuracy of perceptron. The accuracy is basically we are counting how many of the predictions we got right. Okay, so if it was 1 and we predicted 1, we are right. If it was 0, we predicted 0, we are right. Otherwise, we are wrong. So NumPy helps us to do that very easy. So I'll say accuracy. So this is going to help us to evaluate our accuracy. And then it's going to take the features that we have, the targets, and then we will say, so we need to make predictions on all the features. So we say self.predict. You see, is this prediction here method that we are calling? And what do we do in there? We calculate the weighted sum, which is the formula you saw, the sigma I to blah, blah, blah. And then we apply the activation function to it. And the activation function means it will return either 0 or 1, depending on the weighted sum. So we make a prediction. So we call self.predict on the features that are coming in. And then we are basically return predictions is equal to target. And then we calculate the mean of it. You see, guys, take time to learn NumPy. I'm telling you the truth. If you want to be any serious with AI, you can't run away from it. This vectorized computation is making me avoid writing a lot of for loops here. Otherwise, this code will be filled with for loops. And if you look at it, you would want to cry. Like, look at the way I'm doing predictions is equal to target. I've made a prediction on all the features. Then by this predictions equals target, it will check each index of predictions with a corresponding index of target. If it is 0 and it's 0, then it's correct. If it's 1 and it's 1, then it's correct. And I'm calculating the mean of that. So it's eventually giving me the average accuracy that I'm performing. I don't have to write a for loop for this, okay? Okay, now we get to the point where we have to implement, why is this thing not scrolling? We get to the point where we have to implement gradient descent, the algorithm that we've been talking about, the one that will help us so that we don't have to do brute force to be able to train our model. So I'm going to say def train. We take our this, we pass it the training data, the Y train. We pass it our X test, the test data, and then we pass it the Y test because we'll be calculating the accuracy. And like I told you, the accuracy is evaluated on the test set, not on the training set, okay? And then we say epochs. And epochs here is anytime you make your model go over your entire data set, it's called one epoch, okay? And because the process is iterative, it needs to do multiple epochs. Sometimes hundreds, thousands, 10,000, depending on the huge, how huge the volume of the data set you are working with. I'm going to give a default value of, let's say, 100, so that if we don't specify any epoch, we go over our data set 100 times. But for this simple data set, it should be less than that. And then we have our learning rate, which I'm going to call LR. And I told you that is a hyperparameter. We use the learning rate to control how fast we make changes to our weight and biases, okay? Because yesterday I showed to you on the graph that if the changes are too quick, we can get lost. If the changes are too slow, then it means we need more epochs to arrive at the global minimum. So this is a hyperparameter. You need to play with it. So epochs is also a hyperparameter because sometimes after a certain number of epochs, your model has not converged. The way you know it has converged is you see that when it converges, your loss will hover around a particular value. The loss will stop reducing. If it hasn't, then the loss will keep reducing. The whole idea is after each epoch, the loss should reduce, okay? So usually we set learning rate to be a value between 0 and 1, and usually it's good to start from 0.01. If it's too fast, then you go 0.001. If it's too fast, then you go 0.0001, like in those succession. All right, so this is where the learning is happening. All this while we are just throwing data, but how does it learn what it takes for something to be vesicular, absitosa, or vesicular? This is where it's happening. And this is the part of the algorithm I'm telling you is data agnostic. If you like, tomorrow I can request from each one of you to record audio of your voice. Just say the numbers 1 and 2 and record it and send it to Eric. Then Eric will bring it. We pre-process the audio and we will feed the audio to this perceptron, and the perceptron will be able to tell us what we say. We won't change this algorithm. We will just change the dimensions because the audio file is going to give us high dimensions. So we just change the dimensions, we subject it to the same data, we train it, and all of a sudden you have a simple model, just a perceptron. And this time we are not using any library. It's only NumPy for vectorized computation. We are not using TensorFlow, PyTorch, or anything, and it's still going to work, okay? All right, I'm interested in seeing the progression of my loss, how the loss is going to change over time. So I'm going to store the losses in a list. I'm also interested in the accuracies. So I will say train accuracies. And by the way, we have training accuracies and test accuracies. The training accuracy, you measure it on the training data, and then you measure the test accuracy on the test data. But never, ever raise your shoulders on train accuracy. Dude, your model is memorizing. It can give you 100% accuracy. The guy has just memorized. Remember that this computer is Google's computer. You don't even know how much RAM it has. But even on your own laptop with just 4 GB of RAM, this data set is so small, it can just memorize it. The models are very silly. They are very silly, especially if you don't do them well. If you just memorize your data, you put in it, it tells you, you put in, it tells you. But you show it something it has never seen, then it will start messing up because it memorized instead of learning. So you measure train accuracy and you compare it to test accuracy. You expect that both of, yeah.
The memorization, has it got anything to do with caching?
Yes, it's just, you see, it is the mathematical calculations that we have in there. Calculate weighted sum, see the output. Calculate weighted sum, see the output. You get it?
Yeah.
For a perceptron, memorization is not really something that we talk about, but for actual neural networks that have giant parameters, it will just take some lazy shortcut. And like the thing is, you see, you are trying to stop training when your loss reduces. So if the model is lazy, with some few weight adjustment, then it starts getting correct answers. Then it means, you see the way the formula is, if it's getting more correct, then the loss will stop reducing. So there is more to, yeah.
So wouldn't that be maybe the fault of the programmer? Because
it is the fault of the programmer, the programmer's knowledge. Because like I showed you yesterday, sometimes it is in a minima, but not the global minima. That is where you need to know strategies that you can use to nudge it small. It's like you have rolled a ball down a hill, and then it has gotten to some point, then it's going up, down like this. With a little bit force, if the hill is not so high, it will climb and begin to fall on the other side. These are all strategies. We call them regularization. And I'm stressing this because for beginner practitioners, they do this and they are happy. Hey, I've trained a model. You show him donut and it tells you he's a dog. Then you begin to cry.
So why do they choose to call it memorization? Because it makes it feel like the computer is doing something human.
It's because we are borrowing things from human, like the way we communicate in ways that we understand, we will understand. So that is why you see, even the intelligence of AI is not like the intelligence of human. Now that you understand the mathematics behind it, you see that the intelligence is not like the intelligence of
I'm actually like, why would they give all these fancy names when you are just doing mathematics?
Yeah, so that they can get a funding.
All right.
You know, when you name something huge, haven't you seen how Ken University students name their useless final year project? Somebody is building a database system, an online transactional. Somebody is actually building a database software for those places that they sell fish. What do we call them? A store that sells fish.
Cold store.
Yeah, cold store. He's actually building a cold store management system, but he say, I'm building an online transactional data management system for mammals with aquatic abilities. Jimmy said, you are building a cold store management system. We just come up with fancy names, then it makes the whole thing look sweet, but you get a move.
Yeah.
Every science is math. Every science is mathematics. So I always say that if I have the opportunity to do a BSc again, I will not do computer science. I will do maths or physics. Then I will learn these things on my own, trust me. Because when you meet a physicist who is good with programming, they are more dangerous than computer scientists, trust me. If a physicist or mathematician, yeah, if a physicist, no, but Eric cannot compete with me in computer science, but he has focused more on electronics. Yes, he is good with general physics, but I'll beat Eric to computer science related stuff. But
let's take a challenge. 1 month.
Don't worry.
Okay, thank you guys. I have to run away. Many thanks for the thanks for the great session, guys. Thanks a lot.
All right, no worries.
Okay, I'll see you. Catch you tomorrow, guys. Thanks a lot.
So now we have to look over the epochs, and then we do what we have to do. So we say for epoch in range. So I'm looking over all the epochs, and this is how we look. So I'll say epochs +1. Why am I doing +1? Because I'm ranging from 1 to epochs. If I range from 0, then that is okay, but I'm ranging from 1 to epochs. So for each epoch, I want to calculate the loss for that particular epoch, okay? So the loss, I'm going to set it to be 0.0. And then I'll also keep my predictions, and that is going to be a list here. We are going to look over the data, and then we make our predictions, and then we do our comparisons. Then now we do for data, and then target in zip. This zip function in Python, when you give it 2 lists, it is going to pair them correspondingly. So there are 2 lists, maybe a list of names and fruits. If you zip them, if you take the first name, first fruit, pair them, second fruit, second name, pair them, and gives it to you as a tuple. So I'm just pairing each row in the X and each row in the Y so that I can loop over successfully. So I'm going to zip my X train and Y train. And this is where you also want to be very careful, because the shapes of NumPy is always the thing that disturbs beginners, okay? So we make our prediction, and our prediction is going to be self.predict. So we call our predict on the data after zipping. So I have my X, I have my Y. For each row, I'm going through each row. That is what makes me complete one epoch. I go through each row in my training data set, okay? Now, the mathematics we did is beginning to show up here. We need to calculate our error, okay? So our error is going to be equal to our target minus our prediction. It doesn't matter if it's prediction minus error or prediction minus target or target minus error. At the end of the day, the squared takes away whether it's negative or positive. So it doesn't matter here. Okay, now we are going to do our dy, dl, dw, and dl, db. But from the, let me see the screen that I shared, the formulas that we calculated. You can see that whether the LDW or the LDB, we still have this y hat minus y, y hat minus y over there when we do the partial derivative. So we want to write proper code so that we don't have to repeat them. So I'm going to call that the update, the y hat minus the y. I'm going to call that the updates that we are going to do. And because either in the LDB or the LDW, we still multiply by the learning rate. I'm going to do that once and for all and reuse it, okay? I'm going to call that update, which is the update we do to our parameters. It's going to be our learning rate times the error that we had up there. And then for the epoch loss, we say it is equal to whatever it is right now plus the square of the error, so that the negative and the positives, we don't care about it. We want to know how much error we are making in each epoch, okay? Then for those of you who know control theory, when you look at this formula very well, this formula. It looks like proportional control. It's like, if some of you know about proportional control, you know what I'm talking about. It's like you have measured an error. And so how, like, if the error is big, then you need to make big changes to affect the X. You get it? Because this error here, you are multiplying, and whenever you are multiplying, like, you are affecting something. So that's just, by the way, to help those of you who are into control theory to also build an intuition from there that this is similar to building a proportional controller. So now we are going to update our weight. So I'll say my weight is whatever it is, okay? Then I'll say update times the data. Which formula is this? This formula is the L, the W, the partial derivative of the loss with respect to the weight. How? Because we have update that times data. What did we have here? You see, X is the data. This is the update because we multiply by learning rate, whether it's B or W. So I've already multiplied by learning rate in update. So I'm multiplying this by X. This is my DL, DW. So see, when you are translating math into code, it is so simple. Sometimes I feel the way they teach math in school should be that we code it. That is going to give people an entirely different appreciation for the things we learn. But let's just now, how much code can they write? So self.bias plus is equal to update. Why? Because over here it is just y hat minus y for the LDB. So we don't multiply it by data, but we have already multiplied it by our learning rate up here. Okay. So now that we have done this, when we finish each loop over the entire data set, we have to calculate our train accuracy. So I'll say train ACC is equal to self.accuracy. So we have an accuracy method and we are evaluating the accuracy on the training data, okay? Then we can also do our test, which we are doing on the test accuracy, on the test data. So I'll say self.accuracy, and then I'm going to do this on X test and Y test. And then now I'm going to append to the list that we created up here because we want to keep track of them to see the projection over time, okay? So I'll say train accuracies dot append the train ACC that we have calculated. And then we also say the test accuracies dot append the test accuracy, okay? And then finally, we append the losses to the, like we append the epoch loss to the losses because we're also interested in seeing the losses over time. So we say losses, which is the list we created up there. We append the epoch loss to it. Okay, so we can print some information to see how things are progressing. For me, it's not so important, but most libraries will do that anyway. So maybe we should also do the same thing. So over here, I'm basically going to print, and I'm going to use formatted test in Python. This is normal Python. But what makes it amazing is, you see, this is running in a loop, and I don't want to print each line on a separate line in my console or the output. I want the next print to override the other to create the impression of an animation, so that it's not like at epoch 1, epoch 2, epoch 3. No, I'll change it in place. This is what I'm doing here with a /r. When you use the carriage return and the line feed in Python, and then you flash the std output, that is the style that you get. We get the type of animation I'm looking for. So I want to print which epoch we are on. So we said for E, so E is the current epoch over all the epochs. So I'm just, you see 1 over 100, 2 over 100, like to see the projection, like the progress that we are making. Okay, so we have, I'm showing you the epochs, and I can also show you the loss. So for the loss, I'm going to show you the loss for the epoch. So I'm interested in showing the epoch loss. And I can also show the train accuracy and the test accuracy. Okay, so I'll say train ACC. So I want to show the train ACC. Let me copy this guy and paste it here. And then I will also show the test ACC, and then I will also do it here. Okay, now after then you need to end it like this. For what the animation I want to do to work, I need to end it with empty string, and then when I finish, I need to flash std output. So system, that's why I imported std. So std out dot flash. This is, it will force the output stream to be flashed, and then we achieve the animation style that we are looking for. And when we finish, I want to return all the important things. I want to return the losses, the training accuracies, and the test accuracy so that we can plot them, okay? So I'm going to return a dictionary. In the dictionary, I have my losses, and that is going to be the losses list. And I also have my train ACC. I'll just call it train ACC, and that is going to be my train accuracies. Yep. And I also return the test ACC, which is the list of test accuracies. I think this should be it. Okay. So we have finished implementing our perceptron. Now comes the moment of truth. This is the hard thing about live coding. You write the code and then you have to run it to see whether it's going to work or not. So I'm going to create an instance of the perceptron. I'm going to call it a model. And because we are using just two columns of data, I'm changing the input them to 2, okay? Then this return here in machine learning, we usually call it the history of the training. So it gives information about the losses, the train accuracies, the test accuracies, and then we can make our plot. So this dictionary here, I'm going to get it, and then I'm going to use it for some plotting. But that is if our implementation works as expected. So I'll say history is equal to model.train. So this is where we are fitting, okay? So model.train, and I'm going to give it the xtrain, the xtrain data set that we created up there, the y-train, I'm going to give it the x-test, and then the y-test, and I'm going to train it for epochs of, let's say, 350, even though if you don't pass it, it's going to be 100. And the learning rate, I'm going to set. So did you see the animation effect that I was talking about over here? Did you see that?
Please.
Pardon?
No, please.
Okay, look at it once again. I'm running it. You see that it will start from epoch 1 of 350, 2 of 350. Like, you see, I did this in a for loop. The question you should ask yourself is, why didn't it print 350 times? It's because I'm doing the printing in place. So look at it carefully now. See. Do you see it?
Yeah.
So that's what you achieve, and most libraries do that. I don't want to. If I don't do this, it's going to print it 350 times, and it's going to be ugly. Okay. Wow, this model is a rather confident model. What is it telling us? It is telling us that it has gotten to the point after 350 epochs, it is not making any error. Of course, it's expected because this data is just 100 rows. It's simple for any perceptron to conquer. And it's telling us that it's making an accuracy of 1.0. So our model is telling us that all the data in the test set, it can classify it correctly based on what it learned from the training set. Okay, let's see what we have for our weight. So I'll say model.weight. So this is what we get for our weight, negative 0. something something, and then this is 0.07, blah, blah, blah. That is the weight that the model has learned. When we train it, after each training, the weight could be different because, see, we initialize it randomly, and gradient descent will start from somewhere and stop from somewhere. So it's possible, but it should hover around something. At the end of the day, as long as it's getting the correct accuracies, it's fine, because there are multiple combinations of weight with the bias, different bias, that will give us the accuracy we want. So you don't stick yourself to expecting one particular weight, okay? So model.weight, and then I will do model.bias. So now we do some plottings, and then I give you some intuitions, then we can take some questions and close. So the bias is also negative 0.47, blah, blah, blah. All right. So now let's make some plots. I want us to plot the loss. And the way you see if your implementation is correct is your loss should fall over time, because when you start with a random weight, you don't know the correct weight. So you should make bigger losses. That as you train, as the epoch progresses, your loss has to descend, okay? So I do, I want to plot, should I do multiple or on just one? Okay, I'm going to do subplot. I wish I can avoid subplot so that I don't confuse you, but I'm going to do it anyway. If you watch my matplotlib videos, you understand. So I am plotting two subplotting. So I can plot on axis 1 and say it is equal to figure dot add subplot. And these things, don't be deceived that everything is in my head. These are things I've done over and over, and there are some things I'm even making reference here because I've already prepared it. So just don't worry if you start and everything is not coming in your head like that. So ax1 dot plot. So I'm plotting the history, and I'm interested in what? The losses. Remember that over here we return losses to the dictionary. So I'm getting the losses part here, and I'm plotting it, okay? And I want to plot that in a color of red. And I'll set some labels. So I'll say ax1 dot set x label, and I want my x label to be epoch. So the epoch is on the x-axis, and then I can say ax1 dot set set y label, and on my y I'm going to plot my loss, okay? Then now I come to plot my second thing. So on the second, I am going to actually make two plots on one axis, okay? So my second axis, which is ax2, is equal to figure dot add subplot 1, 2, 2. Now this 1, 2, 1, it means I'm making subplot 1 row, 2 columns, and I'm targeting the first cell. This is 1 row, 2 columns, the second. So when we finish, you see 2 plots side by side, okay? So I do this, and then I do ax2 dot plot. And over here, I'm interested in plotting. Okay, we have 10 minutes. We finish. I'm interested in plotting the history, and I'm interested in the train accuracy. So I want us to see the train accuracy, and I'm going to do that in the color blue, and then I will give it a label of train ACC, so train accuracy, okay? Then I'm going to do the same thing. I'm going to plot for the test accuracy. So over here, I'm interested in test ACC, so I copy this, I put it here, and I'm going to label it test ACC. And I will do AX2. I need a legend because I'm making multiple plots on one axis. And then I will copy these guys because we have just 10 minutes for this session to end. And then I'm going to plot the epochs and the accuracy over here. And I need to change this to AX2 and this to AX2. Then I run this. X2, where is X2? Oh, AX2. All right, so you see, it tells us that when the model started at epoch 1, it made an error, like the total loss was greater than 35. Like when it summed all the mistakes, it means it was mispredicting, it was misclassifying things quite a lot. And as the epochs progressed, you see that it got slower and slower until it got to 1. Because I did 350 trainings, that's why the graph looks like that. But if I choose to plot maybe, let's say the losses, if I choose to plot just let's say the first 100 epochs. Let's see. I think it learned rather pretty fast. Maybe even by the 20th epoch, it has finished learning. Like I said, the data set is not, yeah. So now this is a better graph for us to see. So I was just chopping the first 20 for us to see what happened. But you can see that it started somewhere above 35, reduce, and then it got to 0. Now over here, when the curve is flat, we say it has plateaued. When it plateaus, it means the loss is not going to improve any further. It means the weight and the bias that the model has reached is enough to make it do better, like very quality prediction. So you are not making losses. It is hard that you ever get a loss of 0.0. It's possible on this data set, it's very simple, but in real life, you get close to 0 or sometimes even 10, depending on your problem, you are okay with where your loss plateaus. And over here, I'm looking at, I think I plotted them in the same color. I'm plotting the training accuracy in blue and the test accuracy in green over here. So I'm going to run this again. And you can see that the test accuracy, it's raised 1 faster. Why? Because it's like, look at this. There was this training data. That one didn't get there because we were making nudges, but at the end of the day, they were all getting to 1, which means 100% our model is sure that it knows how to predict. Let's do one final visualization. I want to see how our model will actually draw the line between the two data sets that we had, and then we take some questions. To do that, I'm going to import what is known as ML extend. Is an extension for plotting that helps us to do what is known as a decision boundary. So I'm going to import plot decision regions. Yeah. Okay, so there's a function that does that for me already. And we just call that function. I'm not interested in what it returns, so I'm putting the underscore there. And then I'll call plot decision regions. For this, you need to give it your model, your X data, your Y data. It will use the model to make predictions and plot for you. Our models, the data is in X, Y. Like we already have this X and Y up there. We did all those things. Then you need to tell it your classifier that my classifier is the model instance that we have trained up there. If everything is okay, look at this. This is beautiful. So I told you that the perceptron should be able to draw a line that separates the two. So our perceptron is telling us that, see, when you plot anything in this blue region, assign it to this class. Anything in this, I don't know whether it's yellow or orange region, assign it to this class. And because the thing is working, no matter how many times we train it, we get it. So I train it again. After 350, then it still gets that. Let's see if I train it for just 5 epochs, what nonsense is going to give us. Okay. Do you see what's going on? After 5 epochs, our model is actually fooling. Look at what's going on. It actually started by making an error somewhere close to 20. Then it kept rising and rising and rising and rising and rising. So now, instead of the error reducing, the error is climbing. So it's telling you that 5 epochs is not enough for gradient descent to converge. So these are why you need to make your plot. And look at this. You see, if your error is climbing, your accuracy should descend. So mathematics doesn't lie. Our error is climbing, so our accuracy should descend. But if our error is descending, our accuracy should climb. This is the beauty of mathematics. So just in case you see this, then you know, maybe my epochs is too small. That is what makes these hyperparameters. Okay, let's go to 20 epochs and let's see what happens after 20 epochs. Well, it looks like after 20 epochs, the model is perfect after 20 epochs. It looks like it. Yeah, it looks like it. And we plot and we get our line down there. So it means this model doesn't need so much training. I'm going to pause here. And if you do have questions, which I believe you have several of them, let's answer them when it ends. Or maybe, Eric, let's end this and join the other one and take some questions for 10 minutes, and then we finish. Okay, so see you.
See you guys.